let's continue our discussion of the extreme value theorem here. We're going to take a look at the equation negative x cubed minus 6x squared minus 9x plus 2. We're going to look at it on two different intervals and see if we algebraically can identify the extreme values here. So in order to identify extreme values, remember those can happen where the derivative equals 0, where the derivative is undefined, or at one of the endpoints. So I think our first best action here is to find the derivative. So that would give me negative 3x squared minus 12x minus 9. I'll set it equal to 0 and factor out a 3, and this is to find our critical points. Now, if I'm looking for relative max and mins, I would go ahead and put these on a number line, and I would do positive and negative, test the first derivative. But I'm not looking for relative max and mins. I'm looking for absolutes. So all I really care about is that y value at the point. And I'm going to test these critical values. I'm going to end the function. And then I've also need to check the endpoints. Now, one of the endpoints happens to be a critical value, so that's fine. But we're going to go ahead and check the other endpoint. All I need is the absolute highest y value and the absolute lowest y value in order to be able to identify which one is my absolute extrema. So notice, friends, that I am plugging these into the function. I want the y value here. So this is a positive 27. This is minus 54 plus 27 plus 2. That looks like that y value is 2. Okay. Then I'm going to put in a negative 1. Again, putting it into the function. And so I've got positive 1 minus 6 plus 9 plus 2. And that's 6. And then I'm going to put in negative 4. And let's see, that's positive 64. Minus 96, had to think there. Plus 36 plus 2. So that's 100 minus 96 is 4, plus 2 is 6. So it looks like my absolute max is at negative 1, 6 and negative 4, 6, because they have the same y value. So they're the same height. And my absolute minimum is going to happen at negative 1, positive. Nope. At negative 3, positive 2. Okay. Now, if I change the interval to negative 4, positive 1, then of course I only want to use, I'm going to use my critical points, but I'm also going to add that endpoint of 1. So I'm still using my negative 3, which came out to be 2. I'm still using my critical point at negative 1, which came out to be 6. I'm still using my endpoint at negative 4, which also came out to be 6, but now I'm adding an endpoint at 1. And let's see what that gets me. So that's negative 1 minus 6 minus 9 plus 2. So negative 1 minus 6 is negative 7, minus 9 is negative 16, plus 2 gives me negative 14. So notice that my absolute minimum now has changed, but my absolute max hasn't. I still have an absolute max at negative 1, 6 and 4, 6. Oh, sorry, negative 4, 6. And my absolute minimum now, though, is at 1, negative 14. So when you change the interval, you must also consider that your absolute extrema possibly might have changed. Okay, let's then look at possible that the extreme value theorem might not apply. So look at h of x here. We're told on the interval from -5 to 0, h of x is 3x plus 2 over x plus 3. Now, the reason EVT, extreme value theorem, doesn't apply is because h of x is not continuous at -3. Why not? Because if you put in -3 in the denominator, you're going to get 0 in the denominator, which means that on this interval from -5 to 0, this is not continuous. Okay? Why is g of x? Why does the extreme value theorem not work for g of x? Well, it's again because g of x is not continuous. So g of EVT doesn't apply because g of x is not continuous. From -5 is less than or equal to x is less than or equal to 0. Now the reason not, because look at your domain. Your domain says that x minus 3 has to be greater than or equal to 0. We know that because radicals have to, what is underneath a radical has to remain positive. So that means that what is underneath there, x would have to be greater than or equal to 3. -5 to 0 does not work there. Okay? Now look at f of x. I want you to check a look at the domain first, okay? We know that inside of a logarithm must remain positive, meaning it must be greater than 0. Can't handle ln of a negative number, can't handle ln of 0. So that means that x would have to be greater than -7. On this interval, x is greater than -7. So EVT applies on this interval because on this interval, f of x is continuous. It's not continuous everywhere, but it is continuous on this interval. And that's all that EVT requires, that you be continuous on that interval. So watch for your domains there. It's good domain work to see if you're actually going to be able to apply it. Okay, so now we're being asked to determine the absolute extrema on these functions if it applies. If it doesn't apply, then we don't have to explain. Okay, um, so we're pretty good here and here with your domains, right? We don't have any problem with domain here. We don't have any problem with domain there. So let's go ahead. Remember, we're going to find our derivative, then we're going to find our critical points. So my derivative, 3x squared minus 4x minus 3. I'll set it equal to 0 to go ahead and find my critical points. Whew, let's see if we have, if does it factor? I don't think it factors. So this doesn't factor. Let's go ahead and then use a calculator. I'm going to switch my format to this layout so we can use Desmos. I'm going to put that derivative in here, 3x squared minus 4x minus 3. And you can see I've got my values here. So I've got that x is going to be negative 0.535. Now, if you're using the 84, you definitely can find this value as well by using the 0 method on the graph. And then I'm also going to get this value, which is 1.869. Now, remember, we're not concerned with any other values. We're concerned only with the critical points and the endpoints. So I'm going to go ahead and plug these into the function. And I'm going to make sure I do those endpoints. Now, friends, these values are not going to come out pretty. That is A-okay, but I need them to go ahead and find the values. So again, I'm going to use Desmos. That's why I'm hanging out on this screen here. Remember, I had negative 0.535 to the third power minus 2 times negative 0.535, oops, to the second power. Then I've got minus 3 times negative 0.535, and then minus 2. And see the beauty right there is that Desmos gives me that value. I've got negative 1.120. Remember, 3 decimal places for AP. Then I can go back into my statement here and now change because I want to do this for 1.869. So I'm just going to go back here and change those values, 1.869. There we go. And I get negative 8.065. Okay, now same thing then to put in negative 1. One thing I love about Desmos is I can just change it up a little bit. And I get negative 2. And last one here, friends, I'm going to put in 3. And I get negative 2 also. Okay, so where are my absolute max and mins? So I've got an absolute min at 1.869 and negative 8.065. And where is my absolute max? My absolute max is at the negative 0.535 and negative 1.120. Those are my absolutes here. Okay, let me switch my layout back so you can see a little bit better. We might keep Desmos on hand. We might need it again. We'll just have to wait and see. Okay, let's look at number 2 then. And we're going to take the derivative just like we did before. Chain rule. So I've got 2 sine of x times cosine of x, right? Derivative of the outside, 2 sine. Derivative of the inside, cosine. And then minus sine of x. And we'll set those equal to 0 in order to find our critical points. I would factor out a sine of x, it looks like. Leaves me with 2 cosine minus 1. So I've got that sine equals 0. And I've got that 2 cosine of x minus 1 equals 0, or cosine equals a half. So where is sine equal to 0 on this interval? Sine is going to be equal to 0. And I'm thinking unit circle, friends, okay? So I'm going from here all the way around to here. So the sine is equal to 0 at pi, and then again at 2 pi, which is an endpoint, so we'll leave it. Cosine is positive in quadrants 1 and 4, but we're not dealing with quadrant 1 based on our interval, so we're dealing with quadrant 4. Draw my reference angle, my reference triangle. Cosine would be 1/2. So I know this side has to be negative square root of 3, so my reference angle is a 60. The whole angle would be 360 minus 60, which is 300, but in radians would be 5 pi over 3. Just a little bit of review of trig work there, okay? Now we plug them into the function. So I've got pi, I've got 5 pi over 3, I've got pi over 2, and I've got 2 pi. Okay, so pi. Sine of pi we said was 0, so that's 0 squared. And cosine of pi is negative 1. I've got 5 pi over 3, which I've already got drawn. So sine there is negative square root of 3 over 2, but we're squaring it. plus cosine, which is 1/2. So I've got 3/4 plus 1/2, which is 5/4. Then I've got pi over 2, which is at the top. Sine of pi over 2 is 1. We're squaring it. And cosine is 0. So we get 1. And then 2 pi, which is here. Sine of 2 pi is 0. And cosine of 2 pi is 1. So we get 1. So let's summarize. I have an absolute max at, let's see, it's going to be at this 5 pi over 3, 5/4. I've got an absolute min at my pi -1. Okay. So good work with trig functions there, just to kind of keep up our skills and make sure that we're using our unit circle, using our reference triangles to find our values. Okay, friends, let's take a look at number 3. And I'm hoping some red flags are going off. Some warning bells are saying, hey, 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 we got problems. Okay. Because you and I have talked a little bit about this graph of something to the 2/3 power. If you'll remember, it looks something like this, right? And we called this a cusp. Now, the problem with that is that the derivative doesn't exist there, okay? It's continuous, but it doesn't exist. So when I go to find my critical values, but I'm taking my derivative, I have to look not where the derivative equals 0, but I'm looking where the derivative doesn't exist. So I've got a critical value at x equals -2. So meaning it becomes one of the values I check along with my endpoints. Okay, so when I plug that in, I get -2 plus 2, which is 0, to the 2/3, which is 0. Then I plug in -3, which is -3 plus 2 is -1. Square it gives me 1. Cube root gives me 1. And then I put in 6. So that's the cube root of 8 and then squared. So remember, when you have a fractional exponent, it's the power on top, the root on the bottom. Think of the roots of the tree on the bottom. Cube root of 8 is 2, squared it gives me 4. So my absolute minimum happens at -2, 0, but my absolute maximum happens at 6, 4. All right. Last one here as we wrap up for this section. Um, we're doing the ln. We know we've got problems with the ln, so I've got to test and see if it's actually continuous on this interval. So I know that the x squared minus 4 would have to be greater than 0. And so I know that I've got 2 and -2 when I factor. So what part of this actually exists, right? So if I use -3 over here, I get a negative and a negative, which makes it a positive. So we're good there. If I use 0, I get a positive and a negative, which means I can't work there. And if I use 3, I get a positive and positive, so it works. So my function doesn't exist between -2 and 0. That's a problem. So EVT doesn't apply because h of x is not continuous on this interval. So I hope that helps with our extreme value theorem. We've got some good work here with finding critical values, finding your absolute extrema, using those endpoints. Continue to practice with problems like these so that you're a little bit more comfortable with finding each of those values. Bye for now.